Okay. All right, so first of all, if you notice during your practice exam, the ACS is kind of sparse with the conversion factors that they give you. So let's talk about the ones that they expect that you have down. Okay, hold on a second, this is glitching out. Let me just reset. Cool. All right, so first of all, one of the ones that they expect you to know is that prefix kilo. So if I have 1 kilogram, how many grams is that? 1,000, right? 10 to the 3, or just quite simply 1,000. Okay? The other one is that milli prefix. So let's say a milliliter and a liter. What is the relationship between these two? 10 to the negative 3. So there's a few different ways to think about it. You could say that 1 milliliter is 10 to the negative 3 liters, or you could say there are 1,000 milliliters in 1 liter. Both of those are mathematically equivalent. Okay? A lot of people actually find it a little bit more helpful to remember the second one. The first one was what was on our constants page. We learned how to use that constants page. But right, we kind of had a format because we wanted to apply it to any one of those metric prefixes, the ones that we don't know. This is one that you encounter over and over and over again, so it's just kind of a helpful little thing to have in your head. Okay? And then the other one that was quite surprising is that they expect you to know that 760 number for your pressure conversions. That 1 ATM is equal to 760 torr, which is the same thing. Torr and millimeter mercury are the same. Right? So that's the same thing as saying 1 ATM equals 760 millimeter mercury. They expect you to have that one down. Cool. All right, the next one, we're going to talk about acid naming. And there's sort of like 2 forms of acids, 2 types of acids, 2 buckets that they expect you to know. The first one have this same format, HX, all right, where X is a halogen. Okay, so review time. Which ones are my halogens on the periodic table? Give me an element from the halogens. Fluorine, chlorine, bromine, iodine, that's second to last column. Those are our halogens, all right? So let's take, for example, the one that you may kind of hopefully just know through osmosis of being a chemistry student up until now, HCl. What do we call this? Hydrochloric acid. So there's like 2 different ways to approach this. We could say this is just another covalent molecule, right? So hydrogen chloride. And that is the name of that molecule. That's totally true, all right? But really, we would reserve that for when it's HCl in the gas phase, when those hydrogens and those chlorines are bound together. When we make an acidic solution, when we're talking about acids, when it's within water, those things have dissociated. So we don't really refer to it as hydrogen chloride anymore, all right? Its acid name is hydrochloric acid. And this is going to be true for all of those hydrohalogens. They're all going to follow this same format of hydro, followed by whatever halogen you're talking about, but with this ending ic, acid. All right, so let's just do another one here. What do we think HBr would be? Hydrobromic acid. Yes, absolutely, right? And the good news is that the ACS is not a spelling bee, right? So if you mess up one letter in your spell, that's not what we're talking about. But we do need to be able to sight recognize these things and know what we're talking about. Okay, so yes, this is hydrobromic acid. Okay. All right. The other one, the one that's a little bit more of a pain in the butt, are all going to use our polyatomic ions. So let's go ahead and remember these polyatomic ions we're supposed to know. There were 4 that I told you were like the more important ones of the bunch here. All right, so that'd be NO3 with the -1 charge. CO3 with the -2 charge. Okay, let's see if we can name these here. What's that first one? Nitrate. So these are going to be all of our 8s. This one is carbonate. See if you can give me sulfate and phosphate. So sulfate is SO4 -2, and phosphate is PO4 -3. You know, I just kind of realized, and I hope this isn't going to be confusing, but each one of these does a little step where this goes up charge, and then number of oxygens, and then charge again. Charge, oxygens, charge. Anyways, that was not well thought out and in the moment, so if that was confusing at all, just disregard, okay? Anyways, we're going to take these polyatomic ions and we're going to make acids with them, right? So what we're going to do is we're going to pair them with hydrogen ions. Hydrogen ions have that +1 charge. So if I'm going to make an acid with the nitrate ion, that would be HNO3. All right, again, I'm adding that positively charged hydrogen ion. If I was going to make an acid with that carbonate ion, how many hydrogens would I have to have in my formula? 2, right? Because that -2 charge. Okay, cool. So if we're going to take the nitrate ion and make it into an acid, what we're going to do is take this ATE ending and turn it into an ic acid ending, right? So by that, I mean that this goes from being nitrate to nitric acid. Okay, so this kind of helpful phrase that we keep in mind is that the 8 becomes an ic. Okay, so take a second and see if you can give me the name of H2CO3 given that same logic. Carbonic, exactly. All right, if I'm going to make an acid with that sulfate ion. Yeah, cool. So well, how many hydrogens should I have, though? 2. And then this one, if you said sulfic acid, you know, again, it's not a spelling bee, so that'll get you most of the way there. We do keep that UR on the end, sulfuric, just because it sounds cooler, I guess. There's no real rhyme or reason there. All right, and then what about my phosphate ion? How many hydrogens? 3. Now I need 3. Okay, and again, it's actually not phosphic acid, although that's a pretty good guess. It's phosphoric acid. Cool. All right, so we said that these were the polyatomic ions that you kind of want to start with remembering. And they are by far the most common, okay? And then we said, what if we took this same formula, but instead of being NO3, I made it just NO2 with that same -1 charge. It went from being nitrate to what? Nitrite. All right, there was no such thing as a carbonite, but everybody take a second and give me that sulfite ion and that phosphite ions formula. just going to take away one of those oxygens from our 8s. Okay, so now again, I'm going to take these and I'm going to make acids. And remember, we said above that the 8 becomes ic. All right. Now we're going to turn that ite ending into an OUS, an us ending. So the nitrite ion makes nitrous acid. Right? ITE becomes the OUS. All right, see if you can't finish off the other two here if we made acids with our sulfite or phosphite ion. So I'm going to need 2 hydrogens for the SO3 and 3 for my phosphite ion. So this would become sulfurous acid. Right? Furious over that stupid name. And the other one would become phosphorus acid. Right? And people are like, oh my gosh, it's the end of the semester. I can only fit so much into my brain. Look, if I was a betting man, I would say that this first page here is the only one that you actually have to worry about, all right? But God forbid they throw one of these nitrite ions or something at you. This is how we do our naming for that acid, okay? And we have this little phrase that we use to remember this ite becomes us and 8 becomes ic. We say that the white mouse ate icky cheese, because the ite and the us and then the 8 and the ic. All right, so if you're going to boil it down to one stupid phrase to have in your head to remember, that's a good one there. White mouse ate icky cheese. Cool. All right, the other one, next topic, random topic here, is going to revolve around magnetism. All right, and in particular, you might hear these or see these buzzwords of paramagnetic and diamagnetic. Okay, so first of all, importantly, this concept is going to always revolve around one kind of type of problem that we did, which is those electron configurations, but when you draw those little diagrams, right, where you have the boxes and the arrows in them. This is what that's going to correspond to, right? So if I see either one of these buzzwords, I'm thinking my electron configuration diagrams. Okay, so first of all, what do these words mean? So paramagnetism means that that atom does interact with a magnetic field. And you guessed it, diamagnetism is the exact opposite. That's an element or an atom that does not interact with the magnetic field. so how do we know what's what? Again, if we draw our electron configuration diagrams, it's really easy to tell whether that is representing something that's dia or paramagnetic, because paramagnetics always have unpaired electrons, meaning that one of your little boxes has just one arrow in it. And if something does not interact with the magnetic field, that's because all of its electrons are paired electrons. So all of the boxes on your diagram are going to have two arrows in it. Okay? So let's say we want to know if lithium is diamagnetic or paramagnetic. All right, we'll do one of the tiny ones to make our lives pretty easy here. First thing we need to do is we need to be able to tell what its electron configuration is. Lithium's a 1s2, 2s1. All right. What you're going to see is you really don't have to pay attention to the core electrons because they're all completely filled, right? So the early ones in your electron configuration diagram, you don't even really have to worry about. But if we wanted to draw our electron configuration diagram, we'll be good. We'll put energy here. We'll make our little box for our 2s. And how many electrons am I going to put in it? Just one. So then would lithium be diamagnetic or paramagnetic? Para. So it would interact with that magnetic field. It's got unpaired electrons. Okay? So again, there, like you see these buzzwords, you want to start thinking, I need to know the electron configuration diagram for whatever it is that I'm talking about here, right? That's how we answer those questions. Cool. The other one, the last topic, is going to revolve around bond strength and length. All right, so we sort of briefly pointed out these trends in these bond dissociation energies, but let's just kind of make it clear here. We want to rank a bond from weakest to strongest. If I'm talking about single, double, or triple bonds, which one's going to be the weakest? Single. And then followed by double. And our very strongest are those triple bonds. All right, that's our bond strength. All right, if I'm talking about bond length, all right, the sort of trend is the inverse. Our triple bonds are the shortest, and our single bonds are the longest. Right, so you'll often hear triple bonds are the shortest and strongest. Single bonds are the longest and weakest. Okay, so I'm going to put some compounds down here. Let's look at some Lewis structures. All right. I want you to take a second and try to tell me which one of these carbon-oxygen bonds is the strongest and which one is the longest. Okay, so which one's the longest? The single bond. And which one's the strongest? The double bond, right? Cool. All right, so last thing here. I'm going to say, and honestly, I'm kind of pulling these numbers out of thin air here, but we're going to say that this bond here is 100 picometers. And that this bond here is 80 picometers. All right? Now, we got one more type of bond to talk about here. We did single, double, and triple. All right? But if I were to do the structure for this molecule here, what's called formate, actually. All right, I wouldn't be allowed to get away with just one structure, right? Because I could have put that double bond in either one of these positions. Actually, this has a charge, I'll be good. I have to draw my resonance structures. All right, so including just one of those wouldn't be correct. I'm going to have to include both. And what I'm going to do is change the position of this double bond between these two structures. Cool. We all, hopefully, because we just had an exam on it, remember resonance, right? Cool. All right. So importantly, if I'm looking at one of these carbon-oxygen bonds, let's pick this one right here. Right? It's switching back and forth between being a double bond and a single bond in these resonance structures, all right? But again, saying it's switching back and forth is kind of a helpful way to think about it, but it's not completely true. Both of these structures turn out to be true at the same time because the electron's spreading itself out between both of those positions. So it's not like this bond is going from being long to short and long to short. It's got a fixed bond length. And its fixed bond length is going to be between that of a double and a single bond, right? So this bond here would have a bond length at about 90 picometers, right? Right in between the bond length of a single and a double bond, right? If a single bond's 100, a single oxygen-carbon bond is 100 picometers, and a double carbon-oxygen bond is 80. This resonance carbon-oxygen bond is that number right between those two values, 90. Okay? So what we just want to note is that these resonance bonds have an intermediate bond length. Let's say have a bond length between that of a double and single bond. Okay? Cool. So single bonds are the longest, double bonds in the middle, triple bonds are the shortest. And then if we have these resonance bonds, they're going to be that intermediate. They're going to be between the two, right? Cool. All right. So that is